new properties. Let me just go back and review the basics of logs. Come on. Oh, there we go. Oh yeah, I forgot about this. Someone took, and they took the cartoon and animated it, basically. I guess they must have just created this, themselves. But I thought that was pretty clever. All right, now, before we get into, come on. Why is this thing not behaving? Okay. All right, what I was going to say is, here, watch. Let's say I give you, log base b of x. The answer, I'm just going to call y. So basically I have a log function. If you want to rewrite that as an exponential, the base is b. This base to that exponent, y would be your exponent. So b to the power of y would equal x. I'm saying that's the definition of log. It's just an exponential rewritten like this. Or in other words, it basically is the answer is the exponent. Logs are exponents, we say. So if I said, log base 2 of 8, the answer is 3, because 2 to the power of 3 is 8. So that's the first thing, is know how they're related. Now, if you look at these, here's some basic rules we went over on Friday. The answer to all these is what? On the left column? 0, because 2 to the power of 0 is 1. This is base e. Natural log means log base e. And so e to the power of 0 is 1. And so, in fact, the answer to all these is 0. Whereas over here, the answer is all 1, because 3 to the power of 1 is 3. E to the power of 1 is e. Anything to the power of 1 is itself. Okay, so there's your basic rules. Then we talk about this one. And these, it's easy in a sense. They just cancel each other out. You have a base and the log with the same base. They'll cancel each other out, and whatever left is your answer. And it works both ways. If you do log base a of a to the power of something, then that is just your answer. It just cancels out. It's weird, but it works. Okay? Now, so let's answer the first one. And write these down. The next one, you just have negative square root of 2 is the final answer. And the last one? Because natural log means log base e, so it's the same rule applied. Although I wouldn't, you should just know natural log cancels log base, cancels base of e. Okay? Now look at this. Which of these would the rule actually apply to? One of them works, one of them doesn't. Top or bottom? Bottom, because the bottom one is a power form, right? That's what you need to get, is the rule only applies if you're doing a log of a power form with the same base. And then this cancels, the answer would be x plus 1. Whereas the top one you couldn't simplify, because that is not a power form, it's a sum. Now, here's the new rules. We have log of a product, log of a quotient, and the log of a power. And the biggest thing to realize is that we're taking a single log and break it up into 2 logs. We'll do it backwards and forwards. So if we have a sum of 2 logs, you can rewrite as a log of the product. Look at this. Here's where people mess it up. If I give them a sum of 2 logs, they write as a log of the sum. You can't do that. This is more common. If you have a difference, they know to make it a quotient, but it's supposed to be log of a quotient, a single log of a quotient, not a quotient or 2 logs. So definitely don't do that. Besides which, this doesn't even make sense. In other words, tell me, can you think of any numbers, because this is a number minus another number, can you think of any numbers that you subtract those numbers, and then you divide those same numbers, you get the same answer? I mean, when does that happen? Not never. Almost never. Not 0, because you can't divide by 0. Good guess. 4 and 2 work.
Oh, yeah.
I can't think of anything else right offhand. But usually that doesn't work. And so I'm saying, remember, the whole point of this is this difference of 2 logs gets written as a single log. Okay? So don't misapply the rule. And then the log of a power rule is, well, frankly weird, but very powerful, because it allows you to take an exponent and move it out in front as a factor. Which, once again, this is a power form, so you can move that 2 out in front. The law does apply here. This here is not a power, so the law would not apply. Like I said, just be careful how you apply these rules. All right. I forgot I was going to mention kind of how you associate these in your mind. When do you add exponents? When you're multiplying power forms. When you subtract exponents? When you're dividing power forms. And so most people do a good job at least knowing, like, addition goes with multiplication, subtraction goes with addition, but that's really the why behind it. All right, let's do this one. Now, these first problems, what we need to do first is figure out how to express that number in terms of 2s and 3s. And so we're going to break it down. Look, you can do it one of two ways. I tend to do it this way now, where I just take the 96 and I start dividing by prime numbers as much as I can. You take half of, you take half of again. You can just take half of as much as you, a lot actually. Let me pause on that approach. So you start with a number and just divide by prime numbers. If you prefer, you can do the whole factor tree. So you say, okay, half of 96 is 48. And the factor tree is kind of, I don't know, more freeing. What I mean is here, you really want to stick with prime numbers only. And here, the goal is to get prime numbers. But like 48 is 6 times 8, we know this. And then you break it down more, and you get 2 and 3 here, and you get 2 and 4 here. And you break that down, you get 2 and 2. And if I continued this, I would have taken half of next and gotten 6, then take half of again and get 3, and then divide by 3 and you get 1. And the final prime factorization is 2 times 2 times 2 times 2 times 2. That's 5 2s and 1 3. Which you see the same thing in here. But be careful using the factor tree because it's not in order necessarily. And people just lose sight. They lose factors. And so you should have 5 factors of 2 and 1 factor of 3. And obviously you're focused on the leaves only here. So this is not bad. It's just I tend to use this one now. Either way, we now have our prime factorization. 96 can be expressed as 2 to the power 5 times 3. Which is why we did all that. And then that's log of a product. So we rewrite it as log of the first factor plus log of the second factor. And then the exponents can be moved in front as factors. And we're done. Okay? This one's easier, I think, because 32 is 2 to the power of what? Yeah, and if you don't know, it goes 2, 4, 8, 16, then 32. And I'm serious, if you don't know it by heart, do that. So that's 2 to the power 5. The denominator is just 3 to the power 2. And I'll go ahead and take it slow. You get log of that power form minus log of the other power form. And if you want to skip and just go ahead and write the exponents out in front, it all in one fell swoop, I'm okay with that. But that's what we're after. And I'm going to come back to these. Another way they'll phrase the directions is, it says, write as a sum or difference of logs and express all powers as factors. I'm just saying, that's what is expected on these. You try the next one, by the way. Try this one. And I'm going to be writing, just don't look if you want to try it on your own. Did you get a different answer from what I have up there? Here, watch this. This is it. You're done. If you wanted to factor the 3 out, you could. Understand, you're not simplifying when you do that. You're unsimplifying. Seriously. Simplified, there's no parentheses. So you can factor out the 3, and that's okay. I'll take it. In fact, watch this. Because I want to show you another approach you could have taken on this. What's inside the parentheses can be expressed as a single log. It's the log of the quotient. And then if I move this 3 on as an exponent, it becomes natural log of that whole fraction raised to the power of 3. Which is another approach that a person might have taken. They might have said, oh, well, I can rewrite this fraction, 5 cubed over 3 cubed, as 5/3 cubed, and move the 3 out in front, like I did here, and then rewrite this as the difference 2 logs, Those are 3 separate. It's the same idea, okay? These are both correct. This would be wrong. The 3 is supposed to be associated with both logs, either by parentheses or just by writing in front of both, so this would be wrong. Be careful, okay? All right, then there's this one. All right, listen, first of all, 32 is to the power of what? And so the fifth root of 32 is to the power of 5 raised to the power of, that should be a 3 right there. And the third root seen is to the power of 1/3. So we're talking about rational exponents here. So really, the thing is to the power of 5/3. Did you multiply exponents? So I'm saying, really, we're just doing log base 2 of to the power of 5/3. So what is the answer? 5/3. And seriously, on these, if you can just look at that and say, oh, it's 5/3 and write it down without any work, that's fine with me. All right. This one, it's really easy because what is this? Natural log b to the power of 4 is what? Okay. 4. Right? The natural log cancels the base of e. So you get 4 there, 3 times 4. And then this is just 2. And then the 2 is there. So what is the final answer? Because 12 times 4 is 8, last time I checked. So remember, base e, log base e cancels the base of e. You try this one. I guess I should have asked for answers before I gave it away. But hopefully you got 4/3. Same as the last one. One thing I want you to appreciate is, like here it asks for the cube root of 81. We know the square root of 81. That'd be 9. What's the fourth root of 81? 3. 3 to the power of 4 is 81. So the cube root of 81, that's some decimal. I don't know what it is. It's some decimal that goes on forever. It's an irrational number. So it's not like you can figure out the cube root of 81 first or anything like that. You need to take this approach. Okay? All right, then it gets a little different because now it's all variables. Look, first of all, it's a product, log of a product, so we'll start by splitting it up that way. It becomes log base 2 of the first factor plus log base 2 of the second factor. Except, listen, if you have radicals in your problem, go and write them using rational exponents. Like I just applied the log of a power rule, log of a product rule, where log of a product is rewritten as the sum of the log of the factors. And then just move all the exponents out in front, so this becomes 2 log base 2 of x plus 1/3 log base 2 of x minus 1. Except what I wrote is wrong, because the base was x minus 1. If you don't put parentheses around it, it doesn't mean the right thing. So it has to be written exactly like this. Once again, if you write log base 2 of x and then minus 1, then it's the way I just said it, log base 2 of x minus 1. The minus 1 is not part of the argument, but it's supposed to be in this case. Okay? Try this one. It's log of a quotient. I'm just doing the quotient rule and then power rule. And by the way, just don't forget to keep the same base on your logs. It's log base 6 all the way through this problem. And the base was x squared plus 3, so that's your new argument when you get rid of the 2. So once again, parentheses have to be there where I have them. Okay? This is not bad, except you cannot do it the way it's written because you can't do anything with log of the sum or difference, right? So what do? You need a factor. Good. And 1 and 4, I'm thinking? Which one's positive? Yeah. And so there you go. Just rewrite it log of the first factor plus log of the second factor. And once again, you need to have parentheses the way I have them. Where did I mess up, though? Yeah, I forgot the base 7. I'm bad about that. Although, I will still take off. All right, now, yes. These, I'll just tell you right now, the last example here is much harder than this one. This is not bad. In both cases, you're doing log of a quotient. We'll start with that. So it's log of that numerator. Say again? Yeah. So it's log of the numerator. Once again, right radicals is using rational exponents. So it's log of the numerator minus log of the denominator. You're right. Thank you. Okay, really? It seems to not behaving correctly. Okay, so... And then this first one now is a product, so rewrite it as log of the first factor plus log of the second factor. And listen, at some point the exponents when you move out in front of those factors, you could have combined those, skip that step and just written this final answer. It's 3 natural log of x plus 1/2 natural log of x minus 2 with parentheses around it, minus 2 natural log of x plus 2. That one's not too bad. Maybe because we had a product, but the product was in the numerator, so that wasn't too messy. The next one's where it's going to get messier. All right, first of all, we need a factor, because x squared minus 9 can be factored. And so we start with that. If I can write something correct the first time, that'd be nice. And all that is still squared, mind you. So that's my new denominator. And I'm going to just rewrite it. So we end up with log base 5 of the numerator minus log base 5 of that denominator. Did I mess up? Okay. Now, with the second part, you've got a couple of options. One thing you could do, and this whole thing is a power form, you could just move the 2 out in front. You could. Or you could basically distribute the 2, make this squared and that squared, and then go from there. Shania, which approach do you want to take? You want to move the 2 out in front, or get distributed? Okay. So let me just read it. I'll put the 3 out in front as well. So this becomes 3 log base 5 of x minus 2 log base 5 of that product. And frankly, since it's just a product, we don't need parentheses or brackets around it. And now we apply the product rule. So here, let me mess that up. So the log of a product becomes the sum of the logs of the factors. So I said I was going to mess it up. Where did I mess it up, Michael? Yeah. And really, the safest thing to do is I replace the single log with two logs. I would put parentheses around that whole thing. And you don't have to do that. If you go ahead and distribute it, it's fine, but realize it's going to be a minus 2. That is the answer you should have. And you can see I'm distributing in -2. That's one reason. Besides which, look back at the original. Isn't it true that both these, x plus 3 and x minus 3, are both squared, and both in the denominator? So ultimately, somehow, they both should have a -2 in front of them. And so that's the trickiest one of all, obviously. People are going to either not put a 2 or not put a negative sign or not put either. So, and just leave it like that?
Yeah.
I think I'd take either one of those. The most common mistake then is to write it like I had here, but without the parentheses, and then of course it's wrong. Okay, good news is we're going to go from breaking it up into bigger things to combining it, making it smaller. Okay, so now the answers will be smaller than the original problem, rather than exploding. Now here's the deal: we're trying to write it as a single logarithm, and so what we have is a logarithm plus something else. And so before we can combine these, they need to both be logs, and they need to both be log base 5. So you need to ask yourself, 3 is equal to log base 5 of what? And the answer is easy. It's 5 to the power 3. 5 to the power 3 is right. Log base 5 of 5 to the power 3 would be 3, wouldn't it? But what is 5 to the power 3? What number? 125. And then now we have the same base, so we can combine them. And it becomes the log of the product, which is 125x, and we are done. So watch this a second. Let's say we didn't have base 5, we had base 2. What number would go here in that case? 8, because 2 to the power 3 is 8. What if it was base 3? 27, because 3 to the power 3 is 27. So I'm saying whatever base you need for your problem, you take the whole number and rewrite it using a base, so you can work with it. Next one. So the 2 is the problem here. We need to rewrite that log base log base e. So log base e of what is 2? There you go. So we write this as natural log of e squared. Once again, when you're trying to figure things out, you can write it as log base e, but really it's natural log. ln of e squared. Yeah. And this is 2 to the power 3, so that becomes 8, doesn't it? And since it's all addition, the final answer would just have the product of all those, the 8. E squared really should go next, and then the x squared at the end, because we like the variables at the end. And e is not a variable, it's really a number. And I won't take off if you put x squared before e squared, it's just preferred that way. All right, you do this one real quick. Don't look if you want to do it on your own. And once again, if you put log of 2 over log of 25, then shame on you. No, but seriously, don't do that. Don't make that mistake, please, please, please. You're writing as a single log. The rule says this difference 2 logs can be written as a single log of the quotient. Okay? Try this one next. Same same idea, just with variables. And the final answer, if you have rational exponents, I want it expressed as radicals. So don't put x to the power 1/2, put square root of x. Is that okay? All right, this one, I don't know, sometimes it's easier when there's fractions, I mean not fractions, but variables. All right, here, we're going to be kind of methodical here. That becomes 3 to the power negative 2, but what is 3 to the power negative 2? Yeah, it's 3 squared, but it's reciprocal of 3 squared. And then this, of course, is 2 to the power 3, which is just 8. And then you do the product rule. What's 1/9 times 8? 8/9. Once again, mentally, you can do it like that if you want. Or it's just 8 times 1/9 is 8/9. 8/9. And then finally, it's minus this other part that was sitting there waiting. Here's where you got to be careful. It's quotient, right? It's quotient rule. So I'm going to go and write it as a quotient. It's at 8/9 divided by the second argument. But you should never divide. Okay, hold on. Let me try again. Log base A of 8/9 divided by x squared plus 1. Yeah, I wouldn't even write it that way. So rather than dividing by this, I'm going to write it as multiplying by the reciprocal. So you still have the 8/9, but now it's times the reciprocal of that, which is just 1 over that. So like from this, I would just go directly to this. And really just the numerator is 8. And the denominator, you can keep the 9 as a separate factor if you want, I don't care. So either like that or 9 times x squared plus 1 is the denominator. So there you go. Okay. This is kind of interesting. Well, either 9x squared plus 9 or 9 parentheses x squared plus 1. Either way. All right, this one, like I said, isn't too bad. Well, I say that. Look, you're raising to the power negative 1, really, right? So isn't it just the reciprocal? I'm going to be really slow about this. That becomes e to the power of negative, x to the power negative 2, which is just 1 over x squared. Ideally, you can just look at this and know it's going to end up like that. You didn't have to do any of that work. But it shows much work is necessary, so you know for sure what you're dealing with. All right, I'm going to take this a bit at a time. We're going to multiply these. This becomes the numerator, so you end up with x plus 3 over x squared. Because once again, x plus 3 just treated like it's the numerator. And then let me bring down this last part and do the same thing again. You're multiplying these arguments, but this treated like it's part of the numerator, so you get, and I'm going to keep this a separate factor though. In large part because now we have a common factor of x. And if you multiply 3, you might lose sight of that. So this x cancels out, leaving an x in the denominator. So you actually get to simplify it. Okay. And you just get x plus 3 over x when you're done. And once again, you don't show the work look at it quite as much as this. You got to show some work. You gotta. That's good grammar. All right. And there's this one. What should we do first? Get out of here. No. Point 2 is which is 1/5, yes. Okay? Now, everyone tell me the answer right now. The answer is -1. Most people, and I didn't mean the majority, struggle with just coming up with a -1. So what have I said? If you're not sure, what you can always do is put a variable that represents the unknown answer. Then you can rewrite it as a power form and say, okay, this base to that unknown power should equal to 5. And at that point, you may realize, oh, it's reciprocal, so the power -1 is the answer. But if you're not sure, if you just go through all the steps, that fraction can be expressed like this. And then multiply exponents, you get -1x for the exponent. Over here, this, of course, was the power of 1. So you set each exponent equal to each other, and you realize at some point that the answer is, in fact, -1. I'm saying, if you can look at this and know the answer is -1, great, write it down. You don't have to show any work at all in these if you're evaluating these. But and a lot of times, just the act of rewriting the power form makes you realize the answer is -1. But do as much work as necessary until you get the answer.
So it's like, the opposite if it was log of 5, log of base 5, 5, where that was 4.
That'd be 1.
But because it's
There you go. And the kind of fun thing is, this is also -1. 5 to the power of -1 is 1/5. 1/5 to the power of -1 is 5. All right. Changing things up. And you don't have this version. Stick with the version that you have in your paper. So the point of the change base form is, if you have a base you don't like, so here we're presuming that B is not a base we want to deal with. There's only 2 bases you really care for. Usually, at least if you want to type in the calculator, only 2 bases most of the calculators can handle is base 10 and base E. So I'm saying the real change of base formula says you can change the base into whatever you want, which is weird. So this problem with the base B that we don't want can be rewritten as log base C of that old argument over log base C of that old base. And what is C? Something that we chose, which is weird, but it works. And since we get to choose, most of the time we choose base E or base 10. Not always. So here, these that you have in your paper, frankly, we don't have the calculators out, so we're just going to rewrite it. I tend to prefer natural log, so you can write as natural log of the argument over natural log of the old base. Type that in the calculator, give you the correct answer. And so this one, natural log of 89 over natural log of 5. That's how you type it in, you get the correct answer. If you prefer, you can use common log. You can say, oh, this is log of 12 over log of 3. That works just as well. It's like this last one. Log of square root of 5 over log of square root of 2 would work. Or use natural log in all of them. I don't care. Of course, you better not do this. You say, oh, natural log of square root of 5 and common log of square root of 2. That will not work. It has to be the same base. Whatever you choose has to match top and bottom. Okay? And like I said, if you have a calculator, type them in, you'll get the answer. The last one, by the way, well, all these, make sure you close parentheses before you divide. Don't mess up the parentheses. Now, there's this one, though. You're going to use change base formula, but you don't need a calculator on this one. This first part, I'm going to rewrite as, I use natural logs. Use common log if you want, I don't care. But be consistent. This one then becomes natural log of the 32 over natural log of 9. And what happens? Yep, natural log of 9 cancels, which means I get natural log of 32 over natural log of 2, and I can use change base formula in reverse now. So now it's log base what? 2 of 32. And you get it written like this, and the answer is, because 2 to the power of 5 is 32, therefore log base 2 of 32 is 5. All right, now, I think that's all you're writing down. Another use for that change of base formula, though, is if you want to graph something in the calculator that the calculator can't normally graph, type it in using change of base formula. So it can't normally deal with log base 2, but if you type in like this, natural log of the argument over natural log of the old base, or using common log, either way, it'll graph it. Which, by the way, log base 2 you should know. I mean, that's 1 comma 0, and this is at 2 comma 1. Then this point would be at 4 comma 2. What is this point? 1/2 comma -1, because log base 2 of a half is -1, because 2 to the power of -1 is a half, right? I'm saying this particular one you should be able to draw without a calculator. But if you want to check your answers, that's how you have to type it in. All right, just a few little extras. I thought this was something else. Ebbinghouse's law of forgetting. So, I think it's pronounced Ebbinghouse's law of forgetting. So once you learn something, your initial performance is, how well you learn at the beginning. So like here, we could say the initial ability was 90. Then after 2 months, this will predict how well you know it, or after a year, how well you know it. So, sorry, I wasn't going to actually. We're not going to do the example. I was kind of cool. I do want to see if you can figure this out, though. So I'll give you a while. Think it through. Do not, you might,